Okay, so we're shifting gears a little bit, and that 3.3 was all about the quadratic function. Now we're going to start solving rational and radical equations. Remember, in a math class, if you ever see the word rational, you need to immediately think fractions. We're solving fraction equations today. And radical equations, that's where we're taking the square root or third root or whatever root of an expression. And so that's what we're going to learn today. Rational expressions contain rational equations, contain rational expressions. That means you're going to have things that have fractions. And we're going to learn how we solve these, or the easiest way to solve these. So, our first example is going to be this x minus 8 over 3 plus x minus 3 all over 2. What you're going to want to do is figure out what the least common denominator is between the denominators they give you, and you multiply everything, and I mean everything, by that least common denominator. It's not just you multiply the fractions, you multiply every single term on either side of that equation by that least common denominator. So, what would be the least common denominator for 3 and 2? 6. Yes, 6 is the smallest number that 3 and 2 both go into. So what I'm going to do is I'm going to multiply every single thing by 6. Now, if you look at that, it says I have 6 times x minus 8. You're like, okay, I need to distribute. But then if you distribute, you still have a fraction. And so this is where I do my simplifying on the front end. That's always how I've kind of explained it. And what I mean by that is I know I'm going to have this times 6 on top. Okay? Well, my denominator is 3. I know that 6 is the same thing as 3 times 2, which means I have a 3 down here and a 3 up here, leaving me with just 2 times x minus 8 on top. And then I do it again for this 6 over here, knowing that it's going to be 3 times 2, but in this time, I have a 2 on top and a 2 on bottom, so those are the ones that cancel, which leaves me with a 3 times x minus 3. And then on the right-hand side, 0 times 6 is just 0. Does that make sense, what I just did? If you don't like that, you can always do the distributing, and you can always do that as well. It's just, it gets more complicated if you distribute the 6, because then you'd have 6x minus 48 all over 3, and you have to recognize then that that 3 goes into both the 6x and into the 48 so that you actually get rid of it. Because the whole reason we're multiplying by this least common denominator business is to get rid of our fractions. And so if all we do is distribute that least common denominator and then we don't actually simplify it, then we don't actually get rid of our fraction at all. Now what I would do is I would distribute both of these. So I'd have 2x minus 16, and then distribute the 3. So I have 3x minus 9. I look for my like terms. 2x and 3x will give me 5x. Negative 16 minus 9 is a negative 25. Add the 25 over, divide by 5, and I get x is 5. Of course, you would always want to check your answer, and in my notes, I do check my answer. No, I didn't. I thought I did. I didn't check my answer. I thought I did. So multiply everything by the least common denominator. I'd say 90% of all of the fraction or rational equations that you're going to use or see today or moving forward in this class, that's going to be the approach you're going to want to take. You're going to want to multiply by that least common denominator. The only time you're not going to want to do that is like the next example. If you have a fraction equal to a fraction and the denominators are the same, do you know what you get to do? You get to cancel them. That's exactly right. This looks all big and scary, but really what we have is x squared equals 9. We just get to ignore them, which is wonderful. Take the square root of both sides, you get x equals plus or minus 3. The reason why we get to cancel them and just ignore them is because when you have a fraction equal to a fraction, you can cross multiply. Do you remember that? Kind of the butterfly method maybe is how some of you have learned it. X squared over x minus 3 equals 9 over x minus 3. So if I cross multiply, then I'm going to have x squared times x minus 3, and then I'm going to have equals 9 times x minus 3. Notice I have an x minus 3 on both sides. And both sides are being multiplied. So if I divide x minus 3 to move it over, I'm just dividing x minus 3 by x minus 3, which makes it go away. Which is why if your denominators are the same, you're able to just completely ignore them. And that's why getting that least common denominator, getting a common denominator is really nice, because then it makes it to where you don't have to worry about a fraction at all. So if you like having notes, sorry, the Elmo is like in the way. That's what this thing is called, is an Elmo. Right here is the note where it says if you have a fraction equal to a fraction and the denominators are the same, you can cancel them or cancel the denominators and just solve for the numerators. It does say beware of any trouble spots, and that's something I hadn't talked about yet. Trouble spots, aka values that make the denominator 0. When your denominator goes to 0, what happens? Your graph has a hole in it, or there's an asymptote in it. There's a problem there because we can't have 0 in the denominator. And so if we solve this and we leave it as this plus or minus 3, we are ignoring the fact that if we look back up here in our original problem, if we plug in a positive 3, what happens? Yeah, we get a 0 in that denominator, and that causes us a big problem. And so we have to, we are doing a rational equation and there's an x on the bottom, then what we're going to have to do is we have to set our denominator equal to 0 and figure out where these trouble spots are. Where is our graph not going to be able to exist? It can't exist whenever there is a 0 in the denominator. And so we have to find these trouble spots, this x minus 3 equals 0. I just took the denominator, set it equal to 0, I solve, and I say, okay, I have a trouble spot when x is 3. That's the only time I have a trouble spot. Any other number you want to plug in there is going to work. But when x is 3, my denominator goes to 0, and I have issues. So x cannot equal 3. But up here, we said, well, x is plus or minus 3. We had that positive 3. So we have to remove that from our solution set. That means our only solution to this equation is x equals negative 3. So we did not have to do this process on the first equation that we encountered because there was no x in our denominator. Thus, there could be no trouble spots. But for this one, there was an x in the denominator, and so we could have these trouble spots. And notice it doesn't matter if the trouble spots, quote unquote, disappear, because whenever I was working through the problem, notice it became irrelevant. Like here, 3 isn't a problem. But even if it's at the very beginning, if there was a trouble spot from the very beginning, we have to get rid of that from our solution set if it comes up as a solution. Does that make sense? Sorry, my nose itch. We'll see that again in the next problem. I feel like I got a hair on my nose. All right, let's look at the next one. The next one's a bigger problem. We have 2 over 3x plus 6 plus 1 over x squared minus 4 equals 4 over x minus 2. So if I asked you to find the least common denominator, I don't think anybody's going to look at that and be like, well, no, it's this. Because it's more complicated when our denominators include our variable. Luckily, you have a nice teacher who's always going to give you ones that play pretty nicely together. They're always going to share something in common. So let's look at these for a second. 3x plus 6. I'm just looking at this denominator. What do you notice about it? Could we factor anything out of it? Okay. If we factor a 3 out, that would leave us with an x plus 2. Yeah? Okay. This bottom, this denominator, is kind of special. It's a difference of squares. Great job. That's exactly right. We have something squared minus something else squared. That means this factors into x minus 2 times x plus 2. That's what it means to be a difference of squares. It's one of our special trinomials. And then over here we just have an x minus 2. But notice how they kind of have some stuff that overlaps. Like this has an x minus 2 and so does this, but then this has an x plus 2 and so does this, and then this just has a 3. Do we kind of see all this kind of overlappage going on? So here's how we're going to figure out what our least common denominator is. First thing we're going to do is I'm going to say, okay, well, I have a 3. And I don't have that anywhere else, so I'm going to write that down. And then I have an x plus 2, but I also have an x plus 2 over here. So I'm only going to write it down one time. If they have something in common, you still only write it down one time. And then I look and I say, well, I have an x minus 2 and an x minus 2. So our least common denominator is all of that. I took the bits and pieces from our denominators that overlapped and I only wrote them once, and the bits that didn't overlap at all, like our 3, I just wrote it down by itself. And I strongly recommend leaving it in the factored form like this instead of saying, well, that's going to be 3x squared minus 12. I wouldn't do that. I would leave it factored out like this, and here's why. Because when I look at 2 over 3 times x plus 2, which is this first fraction with the bottom factored, and I look at this and I compare that to my least common denominator, what is this fraction missing? Yeah, it's missing the x minus 2. So I'm going to multiply the top and the bottom by that x minus 2. Now again, I'm going to leave the bottom factored out. I'm not going to go ahead and distribute all that. But in the top, I can just go ahead and distribute and so on and so forth. I'm going to do the same thing for each of my other fractions. I look at 1 over x squared minus 4. That's 1 over x minus 2 times x plus 2 and 2. So what is it missing? 3. Yeah, it's missing the 3, so I'm going to multiply the top and the bottom by 3. Then my last fraction is the 4 over x minus 2. What's it missing?
3 and x plus 2.
Yep, so I multiply the top and bottom by that. Sorry, I got a little small. I got off-centered. So for my numerators, or my top numbers, I am going to think about distributing all of my numbers. On the bottom, I'm going to leave it, because what are we doing? We got a common denominator, right, for all of these fractions. And what did we just show happens when we have a denominator the same all the way across? Yeah, we get to ignore it. So all of this work just to ignore the bottom. So really what I have here is I have 2 times x minus 2 for that first fraction. And then for the next one I have 3. And then for equals, 4 times 3 times x plus 2. Like I didn't do any distributing yet. I just eliminated my denominators. But I went from that huge, yucky fraction with all of that stuff on the denominator all the way down to this. Algebraically, this is much nicer. So I have 2x minus 4 plus 3 equals 12x plus 24. 2x minus 1 equals 12x plus 24. I'm going to subtract my 2x over. I'm going to subtract my 24 over. So I get negative 25 equals 10x. Divide both sides by 10, and I get negative 5/2 equals x. I don't know if I went off the screen. Sorry, I did. Shoop. Now, we're not done, though. If this was just a regular old equation, we would be done, but this is a rational equation. And so we need to know if that is going to actually hold, or does that cause a problem? And the way to figure out if that's going to cause a problem is to go back up to the very original equation that we encountered at the top, and we need to set every single one of our denominators equal to 0 and solve, because those are where our trouble spots are. So our trouble spots are going to happen when 3x plus 6 equals 0, or when x squared minus 4 equals 0, or when x minus 2 equals 0. That's where our trouble spots happen. So we need to figure out what values of x those are. Subtract the 6, divide by 3. And in this case, we are going to have some overlapping, which is fine. Because you can get the same trouble spot more than once. It doesn't mean it's like double trouble or anything. It just means algebraically you got it more than once. So if x equals 2 or negative 2, we're going to get zeros in our denominators, and that's going to be a problem. But here's the nice thing. That's not what we found as our solution. So we don't have to eliminate anything from our solution set. This is still our solution. These are just the values at which x cannot be. So if we would have found that x is 2, and then we saw that x can't be 2 because it causes a problem, then we wouldn't have anything for a solution. There would be no solution, because any solution that we would algebraically get would give us a trouble spot. So you do have to watch out for those when we talk about rational functions or rational equations. Are there any questions on that one? That one's about as hard as it gets in terms of the complicatedness of finding your least common denominator and everything like that. But again, even though our denominator was more complicated than like 2 and 3, what we ended up doing is we got a common denominator so that we could get rid of it. And it left us with a much nicer algebraic expression or equation. Questions? Comments? Concerns? All right. So let's switch gears a little bit and let's start thinking about rational equations. There is a slight note, like our principle of powers rule. It says for any positive integer n, if a equals b is true, if we know that's true, then a raised to some power, that is a positive integer, is the same thing as raising b to that power. That's also true. Which hopefully maybe weirdly makes sense. Because if I'm saying that I have 4 equals 3 plus 1, well, my a in this case is 4, and my b in this case is 3 plus 1. If I take 4 and I raise it to the second power, and I take 3 plus 1 and I raise it to the second power, aren't I going to get the same thing? Yeah, because the bases of our exponents were already the same. And if the bases are the same and you're raising them to the same exponential power, then you're going to get the same thing out. So the principle of powers, I'm like, I don't know why we had to give it a name. It seems like one of those things that's kind of common sense that I don't necessarily think needs to be spelled out. But your book spells it out, so I spell it out. So there it is. Are we okay if I take the principle of powers off the screen? All right, so when we solve radical equations, what you're going to want to do is you want to get your radical by itself. In this case, the radical is by itself. But if it wasn't, you would want to isolate your radical. Get it by itself first. And then once it's by itself, we're going to think, okay, I have the square root of 3x plus 1 equals 4. What is the quote-unquote opposite of a square root? A square. So that's what I'm going to do. I'm going to square both sides. Because if I square a square root, it goes away, leaving me with 3x plus 1 equals 4 squared is 16. Now I have a nice regular algebraic equation. Subtract that 1 over, divide by 3, and I get x equals 5. You might also see this written in set form like this, where they give you the curly brackets and you put your answer inside. When it comes to radical equations, you do typically want to check your solutions. The reason why is because when we are working through these, we are going to be dealing with real answers. And sometimes you might get an answer algebraically that says, well, I would have -5. But if I plug in -5 into this equation, then what's going to happen is I'm going to get an imaginary answer, and that causes a problem. So that's how you get trouble spots when it comes to your radical equations, is if you get something that will make the part under your radical negative, then that would give you an issue. So in my notes, this is where I actually worked out I do check all of my answers just to be on the safe side. So if you want to make sure that we did them all right, all of them are right for this one. But yeah, isolate your radical, square both sides. Now this one was real easy because all we had was a radical and a number. But what if we have a number plus a radical equal to a variable? They're getting a little bit more complicated. Step 1 is always going to be to isolate that radical. So if I'm trying to get my radical by itself, what am I going to do first? Subtract the 5. And as soon as your radical is isolated, then you're going to square both sides. And I say squared. If this, for some reason, were to be a cube root or a fourth root or a fifth root, you would raise it to that associated power. I don't think you will ever encounter anything like that, because basically what it comes down to is if you can do it with a square root, you can do it with any other root as well, because it doesn't change anything algebraically. So we typically just play around with square roots. But here's where you want to be careful over here on the right-hand side. I've seen this on some of your tests, that you try to do magic math and take a shortcut here, and you try to say that x minus 5 squared equals x squared minus 25. And that's wrong. You didn't do it right. You tried to square it without actually doing what it says, which is x minus 5 times x minus 5. And when you write it out side by side like that, hopefully you realize you got a FOIL. And when you FOIL, you get that middle term that has an x in it. And that's what you're missing if you do it this magic math way up here. So don't do magic math. So if you take x minus 5 times x minus 5, you're going to get x squared minus 10x plus 25. I'm going to move everything that's on my left-hand side over. Since I see that I have an x squared, I'm going to have to start treating this like a quadratic. So then you have 0 equals x squared minus 11x plus 18. Now, you can do whatever method you want to solve that quadratic. You could factor that quadratic. You could complete the square with that quadratic. You could use the quadratic formula. Here's what I'm always going to recommend, though. I always recommend trying to factor it first. Yes, factoring is one of those things that it takes some time if you're not used to it, but the more factoring you do, the quicker you get at it, and the more you start seeing these patterns fall out. It's also very likely that these are very easily factorable. So that's why I always say try to factor first. And I would always probably use the quadratic formula before I would try completing the square, just because even if it's factorable, you can use the quadratic formula and you're always going to still get the answers that are correct. So when you factor, I have an x squared, so that means I'm going to have an x and an x. This sign here in front of my c term is positive. That tells me my signs inside of here are going to be the same. So I look here in front of my b term, and it's negative. So that tells me both of my signs are going to be negative. The reason why I know my signs have to be the same is because in order to get the c term, just like up here, I had to take my last times my last. Whoops, last times last. And when I do that, negative and negative gives me a positive answer. So the only way to get a positive here on my c is for both of my signs to be the same inside. Okay, then I have to think about factors of 18. There's 1 times 18, 2 times 9, 3 times 6. I need those to add together, one of these sets of factors, to give me 11. 1 and 18, that'll give me 19. 2 and 9, that would give me 11. So that's what my factors are. They're going to be 2 and 9. Set each of those factors equal to 0, and I get x equals 2 and x equals 9. Again, you would want to check to make sure that those don't cause problems in your original equation. The nice thing about this equation is it's actually pretty quick to check, and that if I plug in a 2 plus 7 is positive, so no problems. If I plug in 9, it's still a positive answer, so I'm not going to have any problems. If you want to see a longer version, in my notes I do write out the longer version of checking to actually make sure it works. So, questions, comments, concerns? All right, let's do one more. One more Big Daddy problem, if I can find it. There it is. Oh, hold on, go back. I was looking at that, and I'm like, wait a second, there's something wrong there. So when you check, I was looking at my notes, and I'm like, that's wrong. When you check, if I plug in 2, I get 5 plus the square root of 9 equals 2. 5 plus 3 equals 2, which is 8 equals 2. Is that true? No. So sometimes you're going to have answers that even if it doesn't give you a negative, it gives you a false statement when you check it. Okay? So you have to check it. We call these extraneous solutions. Oh, I guess you can't see that where I marked it out. This is an extraneous solution. Extraneous solution. It's a solution that algebraically you get, but then when you test it, it doesn't hold up. They happen quite commonly with radicals. If you get a radical and you get 2 answers, you definitely want to check to make sure not only that you're going to get like positive under the radical, but that you're actually getting a true statement. Because if we did that exact same thing with our So if we tested our 9, sorry, I was looking back and forth between my notes that are slightly wrong. We did 5 plus the square root, I'm plugging in 9, that would be 16 equals 9. That's 5 plus 4 equals 9, 9 equals 9. We get a true statement there, and so that one did hold. Sorry, I tried to move on a little too quickly from that. So you can have extraneous solutions that don't hold up in the end when it comes to our radicals. When it comes to our rationals, what happens if we have those holes or our trouble spots in our graph, and that's where our denominators equal 0. So definitely test. In our rationals, you're testing where the denominators go to zeros. In our radicals, we're making sure that the solutions that we algebraically got actually hold up and give us true statements at the end. Okay, now we'll go on to this Big Daddy problem. This one is as complicated as it can get. And I say it's complicated simply because we have two different radicals going on, and we can't combine them. We can't say, okay, well, we have x minus 3 and x plus 5. We'll just combine those, and we'll take the square root of 2x plus 2. That's not how this works. If what's under the radical is not the same, then you can't combine the radicals. And so what we need to do is we need to get our radicals on opposite sides of the equation. If you have more than one, get them on opposite sides. So I'm going to subtract over this radical 5 plus x. Backwards, x plus 5. So that I have x minus 3 completely by itself, and then over on the right-hand side I have 4 minus the square root of x plus 5. Now, one of my radicals is isolated. My other one is not, but it's the best we can do when we have two of them. So I'm going to go ahead and square it. And this is where you have to be careful and don't do magic math. Just like on the last one, I can't just say, okay, well, this is 16 minus x plus 5. That's not how this works. What this is saying is I have 4 minus the square root of x plus 5 times 4 minus the square root of x plus 5. We got to FOIL that bad boy. There's no shortcut when it comes to this. So I take first, and I get 16. I take first outer, 4 times the negative radical 5, whatever, the radical. So it'll give me negative 4 radical x plus 5. Then I take inner, which will give me another negative 4 radical x plus 5. Then when I take last, that is when my radical will disappear, because I'm taking the negative radical x plus 5 times negative radical x plus 5, which means I'm just going to have x plus 5. And it is a positive because I had negative times negative. Now I'm going to combine my like terms because I do have some. And I'm going to reorder it so that my x is first. So here's my x. And then I have my 5 plus 26 is 21, and I have all of this here in the middle that I can combine together for a minus 8 radical x plus 5s. So now I have just one radical, so I'm going to think about moving everything over to the other side. If I subtract that x over, look what happens to my x's. They completely fall away. And if I subtract my 21 over, then I get negative 24 equals negative 8 square roots of x plus 5. Now our radical isn't quite isolated, almost. I need to divide both sides by that negative 8 so that I have 3 equals the square root of x plus 5. Now it's completely isolated. So now I can square both sides again to get rid of that radical. 9 equals x plus 5. Subtract 5 from both sides, and I get 4 equals x. So this one's more complicated because we had two different radicals at play. And so we have to isolate one radical, square both sides, and when we do that, what happens is we have another radical that ends up getting FOILed out. Then we have to isolate that radical, square both sides again, so you have to do it twice. And you would want to check your solution, which I do here. I plug in 4 into the original problem. 4 minus 3 is 1. 4 plus 5 is 9. Square root of 1 is 1. Square root of 9 is 3. 1 plus 3 is 4. So it does hold. So this is a valid solution to that radical.